Hello, welcome back to this tribology course. This is the fifth lecture in the series, and today we'll be discussing junction growth theory of the adhesive friction. This is a theory that has been developed and propagated by Professor Bowden and Professor Tabor in Cambridge in around 1940s onward. This basically deals with the situation that happens at the interface when the force is not sufficient to slide an object against another object. And this, they describe this as junction growth because there is a small displacement at the contact, and that they have described as junction growth. Anyway, we'll look at more details of this as we go ahead, but this is a unique theory, and this describes what happens at the interface when the force applied on a body is insufficient to cause sliding. Now, in the last class, we discussed a simple approach to adhesive friction. And there we looked at a single asperity with a hemispherical end pressed against a flat surface, as shown in the figure, with a force F. And there is also a tangential force. So if the force is large enough, then there will be plastic deformation. And we can say that the load W is equal to AR, that is the real area of contact, which is a circle in this case, of radius A, AR into PM. PM is the hardness. So under the load W, sufficient enough to cause plastic deformation, we get W equal to AR PM. That's clear enough, no problem. Then we apply a tangential force F. And if the tangential force is large enough, then there will be yielding. So if tau y is the yield shear stress, then F will be equal to real area of contact into tau yield, real yield stress times real area of contact. So we have got W equal to AR PM and F equal to AR tau y. So in a very simplistic way, we divide F by W and we get mu, the coefficient of friction. And substituting the above two equations, we get AR tau y divided by AR PM. And then that gives us tau y by PM. And in most ductile materials, shear yield stress is half the compressive or tensile yield stress, sigma c, half tau y is equal to half sigma c. And also PM, the hardness is around 3 times the compressive yield stress. So if we substitute that, we get 1/6. So this means that for ductile material, we should get a friction of about 1/6. This is a very simplistic way of looking at things. It will never be like this. There will be variations, but this shows a way out of looking at the friction and the contact when there is a plastic deformation of the asperity and the sliding, which also causes yielding at the contact. So equation 1 is a simple approach to adhesive friction. This also was described by Bowden and Tabor. So we take it as it is and then go ahead to see what happens next. In fact, if we want to consider the contact area, then it is never the influence of normal load and tangential force F separately considered. It is the combined action of the two forces that is important at the contact. Now, in this slide, we consider a flattened asperity shown as a part of the rectangle placed against a flat surface with a force W and a tangential force F is acting. So consider when only W or the normal force is acting and there is a plastic deformation. Again, we can say that the hardness PM is equal to W by A naught. A naught is the area produced by load alone. Remember this. Now, when we apply further a tangential force F, the contact area increases. This has been seen and this is true. The contact area increases. And then we have to say that the tau or the yield shear stress at the contact is F by A1. A1 is larger than A naught. This point we missed in the last slide. We took both as AR. W is equal to AR PM, we said, and F is equal to AR tau Y, we said. But that is not exactly true. So we say that the area increases on the application of a tangential force. Now, when both the forces W and F act, then W is equal to P1 A1. Because now the area has increased. So W will be acting on the increased area and the contact pressure may not be Pn or the hardness. It will be different from hardness. So Pn is not equal to Py at P1. So we say W is equal to P1 A1 and F is equal to tau A1. So then again we say mu, the coefficient of friction, is F by W. And we can write tau A1 by PA1 and then cancel A1 and we can write that tau by P1, just as we wrote in the last slide, tau by PM. But here the difficulty is we don't know P1. So it is the combined action of the normal and the shear force that causes plastic or elastic deformation at the contact region. Now this brings in a plasticity condition. We have to now consider a plasticity condition. Now, one of the very well-known plasticity condition is that of von Mises criteria. And this is well known, and it is written as sigma x minus sigma y squared plus sigma y minus sigma z squared plus sigma z minus sigma x squared plus 6 tau xy squared plus tau yz squared plus tau xz squared is equal to 2k squared. Actually here k is nothing but the tensile or compressive yield stress, but we write here k because we wanted to take this as a constant for a given material. Now before we go on to equation 3, it is probably convenient to look at the stresses on an element shown on the right. There are actually 9 elements, but considering the complementary shear stresses, the stresses come down to 6. So now we have got 6 stress elements. Now, if we consider how we come to this equation 3, it is very simple. We consider that the total strain energy at a point on an element is ET is equal to EV plus ED. EV is the strain energy for the volume change, and ED is the strain energy for distortion. Now, if we equate the strain energy for distortion to the strain energy at the tensile yield point, then we come down to equation 3. It's very simple. One can sit down and do it. Strain energy is usually written by half sigma epsilon, and we can write it, write the equation in a very simple manner. And of course, combine the Hooke's law with it. So we take the equation 3 as it is, and we say that K is nothing but the compressive or tensile yield stress. Then again, we are considering mostly ductile material. And this plasticity condition for bondage is usually well suited for ductile materials. Now, if we look at our situation in the figure below here, we have a flattened asperity loaded by a normal load W and a tangential force F. So we have got only one normal stress, let's call it sigma x, and that is P1. As we said earlier, P1 is nothing but W by A1. And tau xy, which is tau, which is F by A1. So if we put this, and the rest of the stresses are 0. If we put this in equation 3, we get P1 square plus 3 tau square is equal to K square. So that's very simple. So this is an equation that applies to the flattened asperity as shown in the figure below here. Now consider the case where F was applied and there was no tangential force, only F was applied. So we have got nothing else but sigma x, which is P0, P0, because there was no A1. So sigma x was W by A0. We have written this before, I'm not writing it again. And all the stresses are 0. So K becomes P0. If you substitute this in equation 3, K becomes P0. So now our governing equation for this situation becomes P1 square plus 3 tau square is equal to P0 square. Now this shows that there is a definite displacement at the contact between two sliding bodies when a tangential force is applied in addition to a normal force. And all this is before sliding occurs. And this is the situation which is described as junction growth. So before sliding occurs, there is a small displacement. And this displacement is in the form of increase in area at the contact. And that's why it is called junction growth. There are more details of this, but we are looking at it in a very simplistic manner. And following Bowden and Tabor, will be going into a little more depth of this. So this slide shows that if we consider the 3D stress distribution and take a flattened asperity in a 2D situation, subjected to a normal force W and a tangential force F, then we have got an equation of the form of P1 square plus 3 tau square is equal to P0 square. P1 is nothing but W by A1. Tau is the shear stress, which is F by A1. And P0 is the pressure when there was no tau, that is W by A0. Okay, with this, we'll go to the next consideration. Now, this picture that is shown in the bottom of the slide is a 2D situation where we are considering the forces in a two-dimensional object. But in reality, we should consider the 3D plasticity criteria. Equation 3 is the von Mises criteria is 3D, but we are applying it to a 2D situation. But to apply it to a 3D situation is a little complicated, and we are not going into this. We are simply changing the constant 3 tau square. We are making it alpha tau square. So we are saying that P1 square plus alpha tau square is equal to P0 square. And it has been seen that alpha is a suitable constant. It has been seen that this works well even for the 3D plasticity situation. So P1 square plus alpha tau square equal to P0 square is the governing equation for a 3D contact growth situation. Now, we are talking about a situation where there is no sliding, and the force is not sufficient to cause sliding. So we cannot say F by W to be coefficient of friction or mu. We define it as a tangential factor phi, and that is F by W before sliding occurs, and after sliding occurs, which is a special case of phi, then we call it mu. Okay, so the situation here demands a new parameter phi, which applies to the situation before sliding occurs. Now, substitute P1 equal to W by A1, tau is equal to F by A1, and P0 is equal to W by A0 into equation 5. And you will see that we can get, it's very simple, just it will cancel out, and you'll see that it comes out in the form of 1 plus alpha phi square is equal to A1 by A0 square. So now we have got two variables. One is phi and one is the non-dimensional area, that is A1 by A0. A1 is the final area and A0 is the initial area with the normal load alone. So now, if we want to consider what happens before sliding, then we must look at how phi varies with the non-dimensional area A1 by A0. And if you work it out, you'll find out that it comes out in this form. I've shown it in the left-hand corner, phi equal to root over A1 by A0 square minus 1 by alpha. But experimentally also, it has been shown that the plot of phi against A1 by A0 becomes a little bit asymptotical. It levels up at some point above, I think about A0 by A15. So this gives us an idea that how friction coefficient or friction factor or tangential factor varies with the junction growth. As we apply load and tangential force together, and slipping is not occurring, sliding is not occurring, then the friction factor or the tangential factor increases and then becomes, and then levels out at some point. So this is something interesting to note, that as the junction grows, initially, when phi is 0, A1 by A0 is not 0. You can see it from the equation here. So the junction growth process governs the friction behavior before sliding occurs. There is a simple factor, and this curve shows that. Experimentally, we have seen that the two extremes, indium alpha is 3, and for platinum alpha is 12. So alpha, we can say that is between 3 and 12. So for convenience, if we assume alpha is equal to 9, then this equation on the left-hand corner, phi equal to phi in terms of A1 by A0, you'll find out that it levels out around A1 by A0 5. That means when the junction has junction grows about 5 times the initial area, then the friction factor or the tangential factor nearly levels out if you assume alpha equal to 9. So this picture on the left-hand bottom corner pictorially shows that if this little girl is trying to push a heavy object and she is not able to push it, then what happens? Then equation 7 applies. Equation 7 substitutes alpha by 9. In the last slide, we have written P1 square plus alpha tau square equal to P0 square. That is equation 6. Now here we replace alpha by 9 because that is a sort of midway between the two extreme values of alpha. And that is more or less a clear definition of junction growth. So this equation 7 shows how the junction grows and how the friction factor or the tangential factor varies with it. It of course rises and then it levels out. So I think that's a to understand and know that what happens at the contact when the force is insufficient to cause sliding. And that is basically junction growth. Now let's look at little bit more into the detail, because we need to modify this equation a little more for going further into a contamination, a contaminated surface. I'll come to that a little later, but let's see that. Consider a theoretical case where there is no normal load. Now this is funny, because we cannot have a contact without a normal load. But just for argument, consider a case where there is tau, W is 0. And then yielding will cause when tau is equal to tau max or the tau yield. So P1 equal to 0 and tau equal to tau max. And we substitute this in the last equation, P1 square plus 9 tau square equal to P0 square. And we get 9 tau max square equal to P0 square. So basically, the equation reduces to P1 square plus 9 tau square equal to tau max squared. Now this is written twice here, but this is what it means, that P0 squared is replaced by 9 tau max squared. Now this equation will be useful in the next case we consider. So let's go through this again. That we have said earlier that the junction growth is, or most normal ductile material is governed by the equation 7, which is P1 square plus 9 tau square equal to P0 square. But taking a boundary condition that if W is 0, we can show that P0 equal to 9, P0 square is equal to 9 tau max square. So we can reduce this equation to P1 square plus 9 tau square is equal to 9. Okay, so let's go ahead to the next slide. Now, whenever there is a contact in air, or unless it is absolute vacuum or very special circumstances, special condition, there will be some contaminant layer, atmospheric layer or some other layer. So a contaminant layer will be there. So basically, if we want to consider junction growth theory, in reality, we must consider a contaminant layer. Now, let's, tau max is the yield stress of the main body, or the asperity, flattened asperity. So the yield stress of the contaminant layer is considered to be much lower than the yield stress of the contaminant of the main material. So let's take tau I as the yield stress of the contaminant layer. So tau y by tau max, let's call it K1. So this is different from the K we used before. That was the yield stress, but this is just a ratio of the two yield stresses, yield stress of the contaminant layer and yield stress of the material. Now, slip occurs or sliding occurs when tangential stress reaches the value of tau I. When the tangential stress due to friction force F reaches the yield stress of the contaminant layer, then only the slipping will start. That's clear. But if it is not, then the normal and the tangential force will be transmitted to the bulk material and junction growth will occur. Junction growth always occurs in the bulk material. Look at the figure on the right. On the right, junction growth will occur on the main material. So if the tangential stress is less than tau y, then the force, normal and tangential force, will be transmitted back to the main body and junction growth will take place. So in this condition, we can say that we can bring in that equation that we derived earlier, P1 square plus 9 tau square is equal to 9 tau max square. This is the equation that we have been discussing in the last slide. From 7, we have got this equation. So we write this equation, and instead of tau max, we write it Ti by K1. The objective of writing it in this form is to transfer the whole equation in terms of the contaminant layer properties. Because we want to see what happens if the contaminant layer is there. So if we write the equation only in terms of the tau max, then it will not be clear what happens if the contaminant layer is there. So we write it like P1 square plus 9 tau square is equal to 9 tau I by K1 square. Now this, if we do a simple algebra, it will come down to equation 9 tau 1 by P1, tau I by P1 is equal to 1 by 3 within bracket 1 by K1 square minus 1 to the power half. Now, in the equation 9, the left-hand side tells you what happens to the contaminant layer. Tau y is the yield stress of the contaminant layer, and P1 is the stress being applied on it, because P1 is the pressure developed due to the normal load on the enlarged area. So if we look at it, look at equation 9, then we must say that at some point sliding will occur, and when sliding will occurs, then the area will go further, and let's call it A2. Look at the figure on the right hand side. So let me explain this again to avoid confusion. Now we have a flattened asperity, rectangular asperity with a contaminant layer, and the initial loading, normal loading, gives the contact area of A0. As we apply the friction force or tangential force F, the contact area increases to A1. Now, this is okay from junction group point of view, but when sliding occurs, it must increase further, and let's call it A2. So for cross sliding, the contact area is A2. So then we have got F is equal to tau I, because it is the contaminant layer, into A2, and load is equal to P1 A2. So here we can write that because sliding has started, so we write mu, that the coefficient of friction, F by W again is equal to phi, but here A is equal to A2 is equal to tau I by P1. Okay, let's leave it there. Understanding that for cross sliding to occur, junction growth must proceed further. Now, let's look at the equation 9 and write it in terms of K1. You see, in equation 9, it was in terms of K1. T1 by P1 in terms of K1. Now we are writing mu, or the coefficient of friction, as F by W, and F by W is Pi by P1. Look at it carefully. In equation right, left hand side is T1 by tau 1, tau I by P1. So mu is F by W, which is nothing but tau I by P1, and hence the right hand side of equation 9 will remain the same. Okay, so we have got equation 10, which is nothing but equation 9 written in a different form in terms of mu, the coefficient of friction, and K1 is the ratio of the yield stress of the contaminant layer and the yield stress of the bulk material. Now look at this equation 10 carefully. If K is 1 means the yield stress of the contaminant layer and that of the bulk material is 1. Then mu will be infinite, that is very high. That is very clear, isn't it? K1 is 1. That means denominator you have got 0. So mu is very large. So if contaminant layer has the yield stress equal to the bulk material, then the coefficient of friction will be very large. Now reduce K a little more, and take 0.95. Then mu will be around 1. This is experimentally found, and more experimental results are given here. When K is 0.8, mu is 0.45, K is 0.6, mu is 0.25. Possibly this will match with the equation. And when K is 0.1, which is very small, and mu will be 0.03, which is very, very low. So that means if you have a contaminant layer which is very soft, then your coefficient of friction will be low, which we know. And that's very clear even from the junction growth theory. So junction growth occurs in the main body, but if we have a contaminant layer, then the situation is a little different. Then we have to look at the ratio of the yield stress of the contaminant layer and that of the main bulk, and we'll see that the coefficient of friction will vary. It will be infinite when k is 1, and as k reduces, the friction reduces. So this is very much in our understanding that the contaminant layer is soft and the friction is low. Now these results we plot and show in this slide. We plot mu against k. And this is actually k1 it should be. That is the ratio of the contaminant layer and the bulk material that falls as we have seen earlier, that falls as k reduces. This k is plotted 1 to 0. So as k reduces, mu falls. And this will, of course, be dependent on alpha, because we have taken alpha is equal to 9. But if we take different alpha, this curve will be parallel, but will be different. For low alpha, the friction will be even lower, but for high alpha, friction will be a little higher. Similarly, we can plot phi against A1 by A0, which we have done before, and we'll see that it increases with K1 and decreases with K, the value of K. And these two gives us the summary of our junction growth theory. The summary is very simple. Before sliding occurs, it is not to be confused with the static and the dynamic friction. It is the small displacement that occurs at the contact before sliding occurs, and the force is insufficient to cause sliding. Then the contact grows, and this is what is called junction growth. This is what the concept Bowden and Tabor came out with, and this applies very well. And when we apply to the real surface with a contaminant layer, that also gives us very realistic value, that when the ratio of the yield stress of the contaminant layer and that of the bulk material is more, then we have got very low friction. So that's all for today. We'll take this kind of thing in the next class further.